Hi, this is ET250, lecture 15. And today we're going to be talking about filters. We're going to continue our discussion on AC signals and look at AC filters. And we're going to cover two main types, a low and high pass filter. We'll describe what a filter is. We'll look at specific examples implementing a filter with a resistor and a capacitor and a resistor and inductor. And we'll look at some simulations just to make sure we have some nice intuition as to what it's doing. Then we'll look at how industry plots a low pass filter, high pass filter on what we call a Bode plot. Okay, a Bode and a phase plot. And a Bode and phase plot actually require some understanding of logarithms, and there's some legacy power and all this stuff. We'll go into details. And they use the dB scale, okay, decibel. You might have heard the decibel scale in sound, and so we'll even talk about, well, what does the decibel scale mean? And we'll look at some simulations of a low pass and high pass filter and how they relate to the Bode plot. And lastly, just for fun, we'll look at a suspension system, which is actually a second order. So you'll have an inductor and a capacitor in the same circuit, and you get some more complicated response, and we'll see a simulation of that as well. Okay, the first thing is, well, what's a filter? And we're going to represent it by this variable G. Okay, and when you hear a filter, you think of like a strainer or something, like you're getting rid of something that's unwanted. So it's a device or process that removes an unwanted component or feature from a signal in our case. And so, like I said, a strainer filters unwanted dirt from water, let's say. And so here's the idea of a filter. You have some black box. Maybe you do, maybe you don't know what's going on inside. You have some input that you do have control over, VI, and you have some output, okay? And so let's say this is like a multimeter or oscilloscope measurement, all right? And we have some gain on this filter. And this filter, remember, these are AC signals. VI and VI are AC signals. And so this filter can change the phase and it can change the amplitude. So depending on the input here, right? And so this is the equation, V out equals G times VI, all right? And so if G is 1, if this filter gain is 1, then they're the same. But if the filter gain ends up being 0 for whatever reason, the output is equal to 0, even if the input is non-zero. And I think you're already getting an idea that this thing, this magical filter, magical filter, is going to remove potentially unwanted things. Sometimes it removes things that you do want. So tuning a filter is actually very important. Okay. So let's recall from last lecture what a sinusoidal AC signal looks like, or how do we at least describe it mathematically? And I can even draw one. So let's say we're drawing this versus time, okay, and we can draw a nice cosine wave. And remember, this is the peak, okay, and the time between here is your period. The period is related to the angular frequency, and this is the phase. It's what shifts it left to right, okay? So what does this VP do? Increases, stretches it in the vertical direction. What does omega do? Stretches it in the horizontal direction. What does theta V do? It slides it, translates it in the horizontal direction. And if we added another plus constant, then it would shift it or translate up and down, okay? So this is our AC signal. That is what this is going to be. And in this lecture, what we're going to be actually looking at is how does the output waveform look like if the omega changes, right? So if I have a low frequency signal versus a high frequency signal, right? What does that look like, okay? And so what you might see is a plot like this. Now we're going to go into a more in-depth Bode plot, but I think you guys get the idea. If I have G, which is this gain, and at low frequency, so if this input has a small number here, then I have a gain of 1. And if I have a gain of 1, the output equals the input. If I am shaking, or this frequency is shaking very fast, a large number here, then what's going to happen for a low pass filter is that the gain will be closer and closer to 0, which means the output gets closer and closer to 0. Okay, and so this is what a plot of this gain looks like as a function of frequency. Okay, now this middle part is what we're going to call the cutoff frequency. And so it's kind of like in the middle. This is the frequency at which it's like kind of, it's like determining, well, am I going to pass it or am I going to cut it, right? And so this is called a low pass filter, which means I'm going to pass the low frequency content, okay? And so if VI is slowly moving, V out looks just like VI. If VI is quickly moving, then V out looks closer and closer to 0. All right. Okay. For a high pass filter, it's just the opposite. And it's well named because it passes the high frequency. It's just the mirror opposite of this. At the cutoff frequency, they kind of have the same gain, but at high frequencies, if that VI is oscillating very quickly, then the output will match and vice versa. Okay, and so this is what that looks like. Slow moving inputs, no output. Fast moving inputs, match. G is closer to 1. Okay. Okay, now here's a nice example. Let's say you had a signal that had a combination of high and low frequencies, right? Okay, a benefit of, let's say, a low pass filter is all this high frequency component would get killed and you would see something like this, right? All the high frequency is filtered out for a low pass filter. Now for a high pass filter, it would filter out all the low frequency stuff and you would get to see all the jaggies. Okay, so hopefully that makes sense. Okay. If we want to look at a circuit of a low pass and high pass filter, there's actually 2 flavors. One you can make with an RC, one you can make with an RL, and they behave exactly the same way. Okay. Now, so in both cases, you have a VI and a VI, and imagine the G is this part or this part. Okay, just like we showed in the first slide. The G is this part here, okay? So look, I have an input voltage, I have some filter, and I'm monitoring some output voltage. Now the input could change, it's oscillating, it's always oscillating. Everything is shaking right now. We're in this new AC world, okay? So notice the order. I have a resistor, then I'm measuring the voltage across a capacitor. Here, I have an inductor, but I'm measuring the voltage across the resistor. Okay, so that's very important. Now, in steady state, now we're going back to our physics, and we're going, okay, what does the inductor and the capacitor behave like? Well, in steady state or low frequency, the capacitor behaves more and more like an open, whereas the inductor behaves more and more like a short, right? Short and open. And so in this case, we have kind of like an open circuit, which means less current flows through here, which means V out equals this by KVL, right? Okay. Now over here, what do we have? If this is more like a short circuit in DC or steady state, then what? The voltage across this gets closer to 0 and V out again equals VI. The same behavior. Now, what about if this is oscillating very, very, very quickly? Well, when this oscillates very, very quickly, the capacitor acts more and more like a short, actually. And the inductor acts more and more like an open. I mean, no, that's not a perfect thing to think about. Remember the VC of 0 minus equals VC of 0 plus. The inductor IL of 0 minus equals IL of 0 plus. You can't instantaneously change the current. You can't instantaneously change the voltage. But you can kind of think of it as like in the high frequency, this is kind of behaving like a short. This is kind of behaving like an open. So if this is behaving like a short, what is the voltage across a short? 0. Okay. If this is behaving like an open and there's no current flowing through here, by Ohm's law, this is also 0. And in this case, where the high frequency, G is approximately 0, whereas over here at the low frequency, G is approximately 1. So this is an implementation of a low pass filter in both a RC and an RL configuration. Okay, let's look at a high pass filter. So a high pass filter has the resistor as the output. Notice the change. And it has the inductor as the output. So really, you could just, monitor that part, and that's the high pass version, and this is the high pass version, right? Okay, so I just redrew it just so it's a little easier, right? Again, this is G, this is G. And we can play the same game. Steady state, low frequency. Again, C is like an open circuit, L is a short. And we can see at low frequency now, if this is an open circuit, then what? This has no current and this voltage goes to 0. If this is a short circuit, voltage across a short circuit is 0. G is 0. Notice the opposite here. G equals 1 over here, G equals 0 over here. Good. Now, what about over here at the high frequency? Again, This is kind of behaving like a short at high frequencies, right? It's like, yeah, sure, fine, let current, right? The spring is deflecting and opening and closing, no problem. This at high frequency though, it's like, it's having trouble allowing the mass to turn, the inertia water wheel to switch directions. So this is behaving like an open, right? It's all due to the physics. The reason why these are behaving the way they do is because of the physics. So if this is behaving like a short, well, there's not much voltage across this, then what? These two by KVL would be the same, and V equals 1. And here, if this is behaving like an open, well, there's no current here. And again, these voltages are the same, G equals 1. So I hope you're getting a nice understanding of the duality between a low pass and high pass circuit. Okay, good. Okay, so what if we were to look at these low pass and high pass circuits on a simulation? Let's check it out. So I'm going to share my screen. And let's look at this first one here. And before I even start it, the first one, what I have is a low frequency signal here. And on top of it, I have a high frequency. The low frequency has a voltage of 5, and the high frequency is just some noise, voltage of 0.5, okay? And it's going at a kilohertz. I have what's implemented here is a low pass filter. And I'm gonna run this. And I hope what you can see is I'm measuring two outputs. This measurement is actually the input. Think of this as the VI. That is the red line here, okay? And I have the output here is the green line. Notice the green line is smoother. It's been filtered out, low pass filtered out. It filters out all the nasty high frequency content from this signal, okay? All right, so let me pause this. The other thing I wanted to show you is this low pass filter. And what we have here is we have a AC waveform. We'll come back to this later. And so you can see for this low pass RC, what do we have going on? Well, as we run this AC is not a fixed signal, it's varying. And what you can see is the green line is the input and the red line is the output. And notice when the green line starts oscillating quickly, what does the red line do? The amplitude drops. And when the green line starts oscillating slowly, notice that the red line matches the amplitude. G equals 1 at low frequency and G equals closer to 0 at high frequency. So this is an RC low pass filter, okay? We'll talk about the phase a little bit later. You can see at high frequencies, just a little foreshadowing, the phase of the output starts lagging the phase of the input, right? The red line is behind the green line in time, it's lagging, okay? And we'll see that. Okay, let's look at a high pass filter. So the high pass filter has the resistor and the inductor. I mean, you could make an RC high pass filter as well, but I just figured I'd change it up a little bit. And so we can see that for the high frequency, high pass filter, when it's slowly moving, the amplitude of the output is going closer to 0, right? Look at this, when it's slowly moving here, right? The amplitude output is gone nearly, but then as it goes faster and faster and faster, you can see that the amplitude of the output here starts to match the input better and better and better. And notice this one, you have a phase lead in this case. The output is leading the input by a certain amount. And we'll talk about more about that later, right? Okay. So hopefully that gives you some intuition as to what's going on with these low pass, high pass filters and how we can actually implement that in a physical system. Okay, so stop this and let's go back to the DocCam. All right. So what we can plot, I mean, you kind of saw how we plotted the low pass and high pass filter. But the thing is, we might be looking at huge frequency ranges, very large, right? So up to 10,000, 100,000 or more radians per second or hertz, right? And some interesting transitions can occur over relatively small frequency ranges, okay? And so what we might have if we use a linear scale, right? We might have resolution issues when we're trying to plot these large ranges, okay? But what we want to do is we want to see large ranges and interesting transitions, right? It's kind of like a video game where if you're like a sniper, right? And if you're sitting on a building and you're like looking out, you can either look outside your scope and you see the entire map, Or once you zoom in, you see the, the little head that you're going to take out, right? It'd be nice if you can do both, if you can kind of get the big picture and the little picture at the same time. Well, that's what a logarithmic Bode plot gives us. It gives us kind of the big picture and the little picture at the same time, okay? And so here's an example of the problem, right? If we're plotting over a large frequency, you might see this, 1, 1, 1, 1, and then bang, it goes to 0. But the interesting part is squished, right? Right. And so what we do in engineering and in industry is we use the logarithmic scale. And I believe you guys have seen these in your other courses, right? Maybe fatigue plots, right? Fatigue plots are the same way. You have like, you're bending some kind of material test sample, bending, you're at 50,000 cycles, all of a sudden it snaps, right? But what we want to see is, well, how did it behave just as it snapped? And so you lose all that interesting behavior if you're plotting on a large scale. So we go to or a linear scale, we go to a logarithmic scale. I also wanted to show you that this is something that industry uses. Here's an example of a current sensor, right? And this is the data sheet. And so you might see this a lot. And you might see a Bode or magnitude plot and a phase plot. So let's see, I'm gonna zoom in here just so that you can see it. Okay, so there we go. And then let me focus, there we go. So look at this, you have frequency in a logarithmic scale and you have the gain. This is defined as the output of the input, right? This is G. And look at this, you have a 0 dB and you're like, 0 dB, why isn't that 1? We'll talk about that. This is like a gain of 1, and then you can see that it falls off. And you might know, well, wait, does that go off to negative infinity? On a dB scale, yes, it does. But we'll talk about that too, that this actually goes to 0 gain, right? But look, this is saying that the gain is falling off at high frequency. So this is a low pass filter, okay? This new one I'm plotting, you kind of mentioned in the simulation, this is a phase plot. And so the phase is actually the phase of the output minus the phase of the input. And so if your phase is negative, that means see, you can see this phase is negative. 0 degrees means there's no phase difference. Theta O minus theta I is 0. So that means these two are in phase. Makes sense, right? But as the phase becomes negative, what it means is the output is actually less than the input. And remember, we talked about the phase. If the phase becomes a smaller number relative to another one, it actually starts lagging. And so the output starts lagging the input in this case right here. And we'll see more of that later. Okay, so this is a gain and phase plot, or a Bode plot and a phase plot. Okay, so this is in industry, and so the whole point is just to make you aware of what's going on. Okay, so let's go here. Okay, good. Back up. All right. So in order to talk about Bode plots and logarithmic scale, let's review logarithms. Let's get on the same page here. And so if we look at the basic logarithm, now I don't know if I'm so happy with the notation for a logarithmic scale. I feel like there could be better notation. I believe there's some good 3 blue, 1 brown lectures. Maybe I'll try to find a link, put in the description. But this is what we got, right? Log of A, x equals B. And still to this day, when I look at this, I just like shudder. I'm like, oh, gross. What does that mean again? Okay. I always have to remember, okay, I have to say this to myself. The log base A of x equals B, which means given an A and an x, the question is, what do I raise A to in order to get x? And B is the answer. Okay. What do I raise A to get x, and B is the answer? God, that is so confusing to think about. I mean, this is true. And so this is equivalent to this, right? You see that? This and this are the same thing, right? What do I raise A to get x, and the answer is B? Oh, I mean, I wish there was a better notation. Like I said, 3 blue, 1 brown goes into this interesting triangle way. But hey, it is what it is. Okay. And now if we do some examples, that's not too bad. If we see some numbers, so let's say A is 10 and X is 100, right? And so what do we raise 10 to get 100? Well, when we see it like this, that's pretty easy. 10 to the, well, it's 2, right? But that would be equivalent to writing this. Log base 10 of 100 equals 2. When you look at this, it's a little cryptic. It's like, whoa, right? Okay, I guess, yeah, 2. But when you see it like this, then it makes more sense. But at the end of the day, we got to remember this, and hopefully this was a good, nice review. We can move on. Okay, so then let's look at a linear scale and compare it to a log scale. Okay, so I'm going to rotate the paper sideways. Let's say we're plotting omega because we're looking at frequency, right? And so let's say omega, we're looking at a bunch of different values here. 1 radian per second, 10, 100, 1,000 radians per second, 10,000, 1 million, 100,000, right? Okay, so on and so forth, okay? Now, if we do log base 10 of omega, what do we have? Log base 10 of 1. Well, the question is, what do we raise 10 to get 1? 0. So we put a 0 here. Okay, 10. What do we raise 10 to get 10? 1. What do we raise 100,000 to, or 10 to get 100,000? 5. Okay, so what we call these on the street, we call them decades, right? And they're decades in this case because it's a factor of 10. Look, 1 to 10, 10 to 100, 100 to 1,000. In this case, they're called decades, all right? So between the numbers, so this is a base 10 logarithmic scale of omega, and every tick is a 10 times increase from the previous tick. Okay, and so I hope you can see, look, we're getting a large range on a very small scale. And look at this. Over here, I get to see resolution between 0 and 1, but I also get to see resolution between 10 million and 100 million. So that's kind of giving that benefit of seeing a large range and also the small details. Okay, all right, so I basically wrote here what I just said. Okay, now maybe we have a question, just as an example. Let's say the human here can hear 20 kilohertz, right? Remember, this is frequency now, not radians per second, but it's easy. The 2 pi gives you that, what do you call it? It gives that conversion factor. So maybe a question is, how many decades would I need on the x-axis to represent this 20 hertz, right? So we know omega equals 2 pi f, right? And what is, remember I had that rant on pi versus tau. 2 pi is 1 tau, 6.28, okay? All right, so omega is 2 pi times 2,000. So that's the largest frequency that we can hear in radians per second. Okay, fine, 40,000 pi, which if we punch it into a calculator, approximately 3 times 40 is 120, right? 120,000 radians per second. And the question is, how many decades? Well, we can look over here and we go, well, look at this, 100,000. It looks like we would need at least 6 decades to represent that number, because that number is going to fall between 5 and 6 decades, right? So log base 10 of a million is 6, great. And we'd need six decades, okay? So simple question, not too bad. All right, now let's keep going on this logarithmic scale, right? So on the x-axis, we're going to use just straight up log base 10 of omega, no problem. And you saw that actually in that industrial data sheet. So if we look at the data sheet, look at this. Each tick here, it's hard, maybe it's a little hard to see, but it has like 10 to the 3, 10 to the 4, 10 to 5. Each one of these lines is a decade. Okay, so that's a decade. Now this one's in hertz, radians per second. It doesn't matter. It's still talking about the same physical quantity of frequency. And so on the x-axis, when we look at these low-pass filters, high-pass filters, we'll do this. On the y-axis, we're going to use this new concept called dB. Oh, gross, dB. But you just got to know what it is, right? It's a legacy idea, but it's also logarithmic. And so that's how we're going to describe G. And don't get lost now. Remember, G right now, we just care about 1 and 0. It could be greater than 1, could be less than 1, right? Okay, so what we're going to do for a dB scale is we're going to combine log base 10, a factor of 10, and power. Oh, interesting. It's really not that bad. Okay, so what you might see is something like this, is 20 log base 10 of G, and then you say log base 10 of omega. That's exactly what we had on this plot, in fact, right? So this is, it does say dB on here. It actually says dB in units right there. It is using 20 log base 10 of G. Okay, interesting. So let's keep going. Let's keep going. So on the y-axis, we're going to use this dB scale for G, and dB stands for decibel. And you've heard of decibel when we've described sound, but I do want you to walk away from this lecture knowing what that means. Okay, like I said, we're going to use log base 10, and then we're going to compare power, right? Okay, so if we compare power, we're going to use G squared. Why do we use square? Well, don't forget that power is V squared over R from physical units. So you have a square in there. So if I square square, I'm going to also square this. That's why we use G squared, right? So in a decibel system, you're comparing the power of two signals, not just the signal themselves. That's important, right? Okay, and the third thing is just the convention for deci. When you see the D for deci, instead of bell scale, it's the decibel scale. Well, the deci just means you multiply by 10. Okay, that's not so bad. And they had their reasons for multiplying 10 just to scale everything nicely. Okay, and so what you have is this. Instead of log base 10 of G, you have 10 times log base 10 of G squared. G squared because of the power, log base 10 for the benefits of the logarithmic scale, and 10 just from the convention. You look at that, you're like, okay. So if I simplify and we use one of our nice logarithmic rules, if I have an exponent in a log, I can actually bring that exponent out. So A up here can bring A up down there. So the 2 here brings the 2 down there. And that's why I have 20 log base 10 of G for a dB scale. Okay, so that's just the history of it. You just got to memorize it or Google it, you know. Okay, so what does that mean? What that means is if I have G as the output over the input, okay, and I just wanted to plot what are all these things. So just straight up, let's say G, and I want to look at some common values. We can easily do G squared. We can easily do log base 10 of G, and we can easily multiply it by 20, which is the dB squared. So that way, if you see some numbers, you know what's up, right? Okay, so let's say we're at a situation like a low pass filter where these two are operating at the low frequency. So the gain is 1, right? No problem. What is the gain squared? 1. What is log base 10 of G? Well, remember the question, 10 to the what number equals G? In this case, 10 to the what number equals 1? Oh, that's 0. Ah, interesting. And if I multiply 20 times 0, I still get 0. So if I go back to that plot here, look how I have 0 dB. That corresponds to a gain of 1. Not too bad, okay? So then let's go next. Well, what if I have a gain of 10? Well, G squared is 100. Log base 10 of G, well, 10 to the what number is 100? Well, okay, so what do we have here? Oh, sorry, 10 to the what number is 10? I apologize, right? We're not looking at the G squared, we're looking at the G. And so this is 10, and then just 20 times this guy is just 20, okay? So on the dB scale, if you see a 20, what does that mean? The actual gain is 10. All right, good. Okay, let's go to the next one. If you have G is 100, then what do we have? G squared is 10,000. And then you go to here, 10 to the what equals 100? Well, that's 2. Good. And then 2 times 20 is 40. Easy. What about 1,000? Well, 1,000 times 1,000 is a million. What do we go here? 3. And then 3 to 60. Okay, so I think you're seeing a pattern here. 1, 10, 100, 1,000, 0, 1, 2, 3. Easy. And 0, 20, 40, 60. So on the dB scale, if you see 20, 40, 60, you know that on the regular scale, it's just 10, 100, 1,000. Okay, 10,000, same thing. Okay, easy. 5, yep, 10, 100,000, 10 billion, right? 100,000 times 100,000, 10 billion. Wow, I wish I had that kind of money. That'd be nice, right? Wouldn't be given these YouTube lectures. Sorry. Okay, so we had 5 here and then 100, yep, good. Okay, here's an interesting thing. What if your gain was root 2? So the output of the input was root 2, which is like 1.4. G squared, that's 2, no problem. And if I do log base 10, so 10 to the what number equals 2? Well, it's 0.15. So 10 to the 0.15 equals 2. And then if I take 20 times that, it's 3. Okay, well, the reason why I highlight this is because this is kind of a common number that comes out. You'll see something like 3 dB, right? If you see 3 dB, that means that the power ratio is 2. That means the output has double the power as the input of the signal. Not the signal itself, but the power of the signal. Okay, let's look at the next one. Now, what if you have a doubling of the signal, right? Gain is 2, which is like the output has double the amplitude of the input. Well, what does that mean? That means that the power has 4 times, right? The power content, okay? 10 to the what number equals 4? Well, that number is 0.3, and 0.3 times 20 is 6. 6 dB is another common dB decibel number, and that corresponds to double the signal. So I'm just bringing up common numbers that you might see, okay? What about 1 over root 2? Well, here's the nice thing. When I take the square, no problem, 1/2, but check it out. When I go a negative on the logarithmic scale, that's also nice, because an inverse of the same number is just a negative sign on the logarithmic scale. So positive 0.15 becomes negative 0.15. That's kind of nice to think about, to be honest, right? So there's another benefit of the logarithmic scale. Maybe I need to put that up early in the lecture. And then I get negative 3 dB. So a positive 3 dB is twice the power, and negative 3 dB is half the power. That's actually a nice way to think about things, right? And then another one here is, well, what if I have 1/2 the signal? I get 1/4 the power. That makes sense. Negative 0.3, and I should see negative 6. So you look at these common numbers. So negative 6 dB means I have half the signal, okay? So these are just some common numbers that you might see on a regular gain, power, regular log base 10, and dB, which is 20 log base 10, okay? Okay, good. All right, so what would that look like on a plot? Just like this. I just took these data and then plotted it in here. Okay, no big deal, right? This is the G scale. Look, this is negative G, positive G. So if I see negative, when you see a decibel scale, maybe the thing that hit home is on a decibel scale, if I see negative numbers, it means it's not negative in the gain sense, because you never actually go below 0. It just means that it's scaled less than 1. Right? Look at these. These are scaled less than 1, right? For the absolute G scale. If I see positive numbers, it means it's scaled greater than 1. And if I see 0 dB, it's scaled exactly at 1. So can you see here, I have G. Look at all these. These are the actual G scalings for these negative dB scale, less than 1. Okay? All right, good. So let's keep going. So I promised you that I would talk about what does the dB scale mean in terms of sound, right? And again, the dB scale always has to do with a ratio, right? It's the output over the input. And in this case, when I hear dB in sound, what you got to think of is the intensity of whatever sound they're quoting divided by the sound of I0. What's I0? It's what we call the baseline intensity. It's a barely audible sound, right? And G is the gain, right? Okay, like leaves falling, like as faint as you can hear, that's what I0 is, okay? So fireworks are in the 150 dB scale range. Well, what does that mean? What does that mean? How would I solve for the actual gain? What I could say is, well, I know on the dB scale that this is equal to 20 log base 10 of G, and I know G is I over I naught, right? Okay, but what is G? Okay, so I can take 150 over 20 equals log base 10 of I over I naught. Is that right? Okay, and then what do we say here? 10 to the what equals this, right? Okay, and so instead of the nice thing about when you have this, you just need to raise both sides to the 10, right? So if I raise both sides to the 10, which I've done here, 10 to the 150 over 20 is 7.5, 10 to the log base 10 of G is just G. I get G is 31.6 million. So that means that this I is 31.6 million times the sound of what's barely audible. Okay, so that's the idea of a decibel system for sound. It's actually in a ratio, and it's comparing it to the baseline intensity. Hope you learned something new there. Okay. All right, let's go back to what we call a Bode plot using the dB scale. We are review logarithmic scale. We get nice resolution, large range. We have a 20 dB, right? Every time you see 20 dB, it means a factor of 10 for G. You see 40 dB, it's 100. You see 60 dB, it's 1,000, right? So on and so forth. 1 decade is every 10 omega. Okay, good. So if we look at a low pass filter, this is what a Bode plot might look like at the low frequency. So what do we have here? Let's just make sure we're on the same page. On the x-axis, I have my log base 10 of omega. On the y-axis, I have my dB scale, 20 log base 10 of G. So 0, 20, 40, 0, minus 20, minus 40. And I have 0 dB here up into the cutoff frequency. And let's say our cutoff frequency is 1,000 hertz, or radians per second, sorry. And so the log base 10 of 1,000 is 3, right? 10 to the 3 is 1,000, good. And let's see, after that, it starts to fall off. Now, these black lines are what we call the asymptotes, whereas the dashed line is the actual. And look at this, at the actual cutoff frequency, you get minus 3 dB. That's a common number we saw. What is minus 3 dB? Well, let's just go back to our table. Minus 3 dB is, I believe, the half power. So at the cutoff frequency, you don't get 0, you get the half power of the output over the input, okay? What do we have? 0 dB. So in the low frequency, 0 dB corresponds to a gain of 1, right? The output equals the input. At the cutoff frequency, yep, I have half power. And when omega gets bigger, what you'll see is the slope, 20 dB or minus 20 dB per decade. And you like that's a number like engineers will throw around. Oh, it's increasing at 20 dB per decade. It's increasing at 40 dB per decade, right? And you want to know what that means. You want to be in the know, right? And it sounds super fancy, right? Especially talk to sound guys, right? It sounds super fancy, but it's not that bad actually, because we know 20 dB is either an increase or a decrease of G by factor of 10. And a decade, as we know, is an increase or a decrease of omega. So if it's minus 20 dB, that's a 10 times decrease in G and 1 decade. So it's just like a 10 for 10, right? So that means a 10 times decrease in G means a 10 times increase in omega. Okay, well, whatever, right? Sounds fancy, but it's really not that bad, okay? Hidden in the obscurity of this Bode plot stuff. But like I said, we're just trying to explain to you what it is. Okay, low pass filter, the phase plot looks like this. So at low I'm still plotting on a logarithmic scale. At the low frequency, the phase is actually starts at 0 degree phase, and then it goes down to minus 90 degrees for the low pass filters. Remember, this is 1/8 of a cycle at 45 degrees, quarter cycle at 90 degrees. And the phase is defined as the output phase minus the input phase. Minus, notice the minus. So when the phase is negative, and I said it before, the output is lagging the input, okay? And so here in a low pass filter, the output can lag the input by as much as a quarter cycle or 90 degrees, okay? We'll see the opposite is true for the high pass filter, okay? So for the high pass filter, look at this. It's just like the flip of the low pass filter, right? We're increasing at 20 dB per decade, and then we get to 0 dB at the high frequency. Again, you get the half power or minus 3 dB point here, okay? And so we have it for every increase of 10 of the frequency, we get an increase of gain of 10 times, right? Okay, yep, everything's the same. So at the high frequency, we get 0 dB gain or 1, gain of 1, output over input. Output equals input. Hopefully not too bad. Okay, so let's revisit the phase plot, and the phase plot is slightly different. Notice at low frequency, we have 90 degrees down to 45 down to 0. Again, if the phase is greater than theta I, the phase of the output, what does that mean? The output is leading the input by as much as a quarter cycle or 90 degrees. So let's look at the simulation again of those things. We saw it already, but let's look at it again with this new phase idea in mind. So share screen. Okay, so go back to the low pass filter. We're gonna run it again. And look at this, I'm gonna pause it. Look at this, we're starting to get higher and higher frequencies. This guy is shaking faster and faster, and look what's happening. The output is decreasing in amplitude, and notice relative to one cycle, it's shifting over by 90 degrees, phase lagging, right? And if we keep it going and we go back and slow it down more and more, or as this input, VI slows down more and more, what you see is that the phase of the output gets closer. Look, So if we were lagging, this red line would be all the way back here. But since we are lagging a little bit, but it's much closer in phase, so the phase difference gets closer and closer to 0, okay? And then as we speed up again, the phase difference gets bigger and bigger and bigger, right? Closer to 90, okay? And we still get that low pass filter. At high frequencies, the output in red is decreasing in amplitude, the input, and as the input decrease in frequency, the output matches, okay, the input, okay, which is in green. Cool. So now let's look at the high pass filter. And the high pass filter, if we look at this plot, notice as the frequency gets slower, look at the phase, it's leading, it's more and more leading by 90 up to, look at the peak of this is happening over here, which is 90 degrees, that's a quarter cycle, right? And then as it slows down more and more, look at this output, it's nearly 0 in amplitude, okay? Now, as it increases, as the frequency increases, notice the output increase in amplitude and start locking together in phase. Look how they almost become synchronized at the high frequency point. Right there, yes. Right, see, no more phase lead anymore. The output is now in sync. Slight, ever so slight phase lead, but they look fairly in sync. Okay, let's go back to the doc cam and look at our last example. This is for fun, but I don't know if any of you are car guys, but a vehicle suspension can be thought of a mass, a spring, and a damper, right? And what you could do is think of the road as the input, bumpy, 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 and the output is something you want smooth, right? And what you might have is another Bode plot. And if you don't tune your damper, right, you don't tune your damper and springs correctly, what you might feel at the wrong road interval speed, you might feel this resonant. And all of a sudden it's like really bumpy, right? Okay, or you can imagine if I had a mass and a spring and I'm like, you know, I'm oscillating the mass, there's a resonant frequency where I'm just right, I'm not even moving much and it's like oscillating crazy. This is the resonance. So you have 0 dB, gain is 1, but once that gain goes above 1, or sorry, 0 dB, the gain is above 1. So let's say it goes up to 10 dB. Well, if I do the whole 20 log base 10 stuff, that means that's a gain of 3.16, that's crazy. So that means an input of let's say 1 Newton meter gets 3 Newton meters, right? Or 1 Newton gets 3 Newtons, or 1 volt gets 3 volts, or 100 volts get 300 volts, right? So what you might see is this bumpy road, right? A little bump of here of 1 centimeter will get 3 centimeters, right? And then if the frequency gets faster, right? You go over a more pebbly road, right? It'll start falling off, and it'll fall off at 40 dB per decade, right? And what does a 40 dB per decade loss means? 100-time decrease in G for a 10-time increase in frequency. So the vehicle, in other words, doesn't feel very, very high frequency. Now, what, of course, you want to do is tune your K and your B values so that it does this, right? Of course. But this is an example of, let's say, Tacoma Narrows Bridge, where you had a second order response and they did not tune it well, and the wind just happened to have the right oscillation and it just destroyed itself, okay? What does the phase plot look like? Well, the phase plot looks like this. So instead of going from 0 to -90, it goes 0 to -180. It goes another, every time you go in another order, you go another quarter cycle, right? So here's a quarter cycle off, here's a half cycle off. That's completely out of phase. When one's going positive, the other is going negative, right? And negative, again, negative means the output lags the input in this low pass filter, second order low pass filter. Why do we call it second order? Because you have kind of two of elements. Remember, a K is like a capacitor, and a B is like, an M is like an inductor, and a B is like a resistor, okay? What we'll see is, in the simulation I'm about to show you, is that I can build a similar, it's the same math, guys, the same math, but I can use an inductor and a capacitor and a resistor all in the same thing and get a second order response. I can get the same response. So it's kind of neat. So let's go back and finish it off with the simulation here. So share screen. So this is the last one here. Now check this out. I have an inductor, a resistor, and a capacitor. Okay, so let me just reset this. Okay, so let's look at what's going on. So the input again is oscillating, and notice low frequency, yay, everything's happy. I have a gain of 1. I'm happy. I'm measuring this output here, okay? And the output is in red, the input is in green, okay? Now this thing is gonna be increasing. This is increasing in frequency, okay? So notice what's happening as this guy's increasing. What do we got going on? Instead of the output actually decreasing in amplitude, it's increasing amplitude. It's starting to hit resonance and the phase is starting to lag, right? Notice the phase is lagging, getting closer. It's going to get as much as 180 out of phase. Look at this. This is increasing higher and higher frequency. This is awesome. This is not good, right? Imagine, you know, this is a vehicle suspension. So at this point, this is the resonant frequency. And if you go start increasing the frequency any further, what happens? Look at, I'm going to pause it here. Look at this resonant frequency. The peak is happening at the 0. So we're at a quarter cycle out of phase. And the peak is crazy high relative to this one. As we keep increasing the frequency of the input even more, now look what happens. The amplitude, sure, it drops off. The red gets smaller and smaller, but look at the phase. The phase of the output is now closer and closer to 180 degrees out of phase, or opposite, completely out of sync with the input. And so we keep running this more and more. Look, it's falling off, right? And hopefully this makes sense. Okay. So I hope this lecture helped. I'll put up the links for all these simulations in the description, and I hope this was enlightening. Have a great day, and see you in class.